This week it has moved to 215. From now on, 215. 215 to 3. It's great pleasure to have Professor Jiehang Zhang, who joined us recently, and he's going to talk about quantum information with ion traps and atoms.
Okay, thanks. So my name is Jiehang, and I'm very thrilled to talk in front of this mathematics audience because I myself come from the background of experimental quantum information science, and I worked both on neutral atoms and ion traps, and so these are systems that are based on the fundamental building blocks of our world, which are the quantum particles we use, for example, cesium, beryllium, these atoms or ions, which are charged atoms, as you know, to really play with interacting quantum many-body systems and see their behavior and use them to simulate complex quantum dynamics, for example, and with the goal of building a scalable quantum computer in the future. So I'll try to give instead of a detailed explanation of my research, I'll try to give an introduction of essentially my field and hope you don't get too bored. Anyway, okay, so this is the brief outline, and let's look at the first part. I call it From Quantum Advantage to Logical Qubits, the battle continues. So this is my favorite way of introducing, and I think it's very amenable to the mathematical audience. That is, we always hear the spooky action at a distance, this weirdness of quantum mechanics, but it's actually nothing more than two quote-unquote simple rules that was prescribed to us. That is, rule number one says quantum mechanics, well, in principle, has this exponential space, and that is because the Hilbert space has wave interference effects. It's because we have to use complex probabilities in order to describe these quantum behavior. And rule number two says rule number one only works when you're not looking. So this is the quantum measurement conundrum that was debated even to a philosophical level for many, many years. But essentially, till the since the beginning of quantum mechanics, Bohr and Einstein debated about this, and essentially until the 80s or maybe 70s in the last century, in the context of single particles, this debate has basically settled. But in my opinion, in the context of many-body physics, it's actually very unclear because you can steer your measurements to be partial and entangle, using your measurements to entangle more of the quantum system. So that's actually a very rich field of research that we're looking into. So yeah.
Painting is the most reproduced piece of art. This most reproduced painting in history of paintings. This one.
That's
Japanese painting.
Yeah, it's a Japanese painting. I think the original might be in the Museum of Chicago. Yeah. Anyway, so
Is it?
anyway, that's just thanks for the interesting note. So where are we right now? So we all heard that we're past the quantum vantage stage, which was first realized by Google using this so-called random circuit. It was a sampling task. Who claimed that they can go beyond that classical computers cannot solve this sampling problem, and a quantum computer with 53 and now 60, 70 qubits in USTC, they can and Google, they can perform this sampling task. Also with also with the photons, one can perform this Gaussian boson sampling with the complexity proofs that under reasonable noise assumptions, one cannot perform the classical simulation. However, in fact, yes.
Back to so many years ago, perhaps, for example, for boson sampling, back to work of Arkhipov in 2000.
That's right. That was the original proposal. That's right. So that was the original proposal was using single photons for boson sampling, and this Gaussian boson sampling relaxed the condition such that you can use quantum resource states such as squeezed states, and you don't have to use single photons. So the single photon sampling, I don't remember the state of the art, but right around the time of this Gaussian boson sampling, single photons, you can only do something like 18 photons, whereas this one you can, right now, I believe the record is more than 200 photons. So it's a slightly different tweak. Yeah.
Quick question. You're going to explain what we are going to do with these photons, right? How does it work? Okay, so I see some lattice of atoms. Okay.
This is so far just an introduction. So I want to mention these experiments because they, well, if you dig into details, they don't really. It's hard to say whether they're advantageous or not, because you see these experiments gives exponentially small rates of the correct answer, and classical computers don't do that. We usually want deterministic. Even with machine learning tasks, you want the sampling to be mostly correct, right? So whereas these quantum machines actually give exponentially small, meaning that part per thousand or even part per million correctness rates. So errors are a big problem, and that's what I want to mention. That is, well, there's a few problems. For example, classical algorithms keep improving. So tensor networks and so on. These algorithms are already exceeding some of these previous results. And the second problem is that because we have such low corrector rates that we cannot verify which results are correct once you're beyond the classical tractability. So this is a bit like there was a English science fiction Hitchhiker's Guide to the Galaxy. In that fiction, there was a supercomputer that can compute the answer to the universe. And after I don't know, millions of years or whatever, it spit out an answer which was 42, and nobody knew what that meant. So it's a bit of an analogy there. So errors, how can we deal with them? Well, we are sort of entering into a dawning stage of this error-corrected quantum computing, which basically says that if we encode physical qubits into logical qubits, then we can use this resource to trade for precision. So basically, it's kind of like a door latch. Once you're above some kind of quantum error correction threshold, the quantum computer can be essentially error-free. But so far, we have proof of principle demonstrations from Google, from this ion trap company Quantinuum, for example, and also from the Harvard group, who already demonstrated IQP sampling, instantaneous quantum polynomial sampling, which is related to the random circuit sampling from the Google work, with 48 logical qubits, and this was with 200 plus physical qubits. It's in fact fairly efficient encoding when compared to some of the codes, for example, surface codes, as adopted by most, for example, solid-state superconducting qubit groups. So there are many platforms which we're attempting to build quantum computers on, and I'm missing some even in this picture. For example, there's still quantum dots, topological qubits, but I would say that some of the main competitors are cold atoms in optical tweezers, superconducting qubits, and trapped ions. So photons we've mentioned before, but the problem with photons is that it's very hard to make them interact. So the previous sampling experiments were all done with resource states previously generated, and then they go through linear beam splitters in order to run the quantum circuit. So it's not exactly a gate model quantum computer, and nitrogen vacancy centers are very good for precision measurements and quantum sensing, and are used to demonstrate some of the earliest quantum algorithms, such as factoring, but sort of a consensus by the field that it might not be the most scalable one. So so we'll talk because I had previously worked on cold atoms and ions. We'll talk about these systems. We'll give a short. Of course, this is to some extent personal view, but we look at some of the pros and cons of different systems. Now, you might have heard a lot about superconducting qubits. They've made lots of progress in the past 10 years. And the gate fidelity is, in fact, has increased a lot in recent years. And they do face a scalability challenge as in, for example, surface code requires lots of physical qubits. Somewhere close to 700, maybe even 1,000, if you want to. It depends on the error distance that you want to correct. So if the distance is 20 plus, it gets to a couple hundred physical qubits for encoding one logical qubit. So that's a lot of qubit space to be thrown away. So if you want to be efficient, we can look at these two systems, which are trapped ions and atoms in optical tweezers. One of them is, of course, charged atoms, and the other one is neutral atoms. And of course, the superconducting qubits, they are artificial atoms. So we always want some sort of atomic properties because, for example, real atoms, they are identical. They are very precise. So they have incredibly long coherence times. With trapped ions, you can get to 1 hour, and you can get to 2 qubit gate fidelity with 4 nines. That's the current record among any physical platform in quantum computing. These are physical 2 qubit gate fidelities. But I have to remind you that this number, 4 nines, is many orders of magnitude worse than classical computers because you can perform a classical gate on a CPU with 15 nines of fidelity, so that you don't get a blue screen, say in 2 weeks, right? Because you have 4 gigahertz clock rate. So 4 nines is not quite good enough, at least in our digital computing model. And so the most difficult challenge, I would say, for ion traps is that the scalability. Currently, the state-of-the-art by Quantinuum, the US company, is based on the architecture called quantum charge coupled device, which I will talk about in a little bit. However, neutral atoms have also long coherence times, reasonably good fidelity, so there's still room for improvement. And the really important part is that it's very scalable. So now, with the real atoms, you both, either with ions or neutral, you have this high connectivity, which means that one can go beyond the nearest neighbor coupling limit. And this really makes the encoding of quantum error correction codes very flexible. So, which means that you can, in fact, move the atoms or ions in order to create high-dimensional circuits and so on. So
can I
also
ask you
touch on
something?
that.
So with these atoms,
Yeah.
the medium is solid. Am I right? With these atoms?
No.
No.
So with these atoms, they're trapped in a vacuum or
In
with laser
vacuum.
fields. Yeah.
I see.
Uh-huh.
So the other one is also
So with
vacuum, but
with
what?
ions, they're trapped in vacuum, but with electric fields because they're charged. They respond to
I
Coulomb.
see. And in very low temperature.
They're laser cooled to basically millikelvin. So.
I see.
Mhm, mhm,
Okay.
mhm. So very good, because I will talk about some of these. So let's look at the ion traps for a little bit. So I did my postdoc on ion traps. Now the high fidelity gate I mentioned 4 nines. That was with microwave fields, and if we use laser fields, we can get to 3 nines and a 4. So this was work in the U.S. Georgia Tech Institute, and so this platform is really a platform for exquisite precision, exemplified also by the fact that they have the most precise clock. So what is a clock, one might ask? So Huygens first created the pendulum clock, which is basically a swing that you can count the number of times it swings in a certain amount of time. So essentially, how one can realize such high fidelity gates and such high precision timekeeping is all because that these atoms have very precise levels that can interact with electromagnetic fields, such as laser fields or microwave fields. And we use these electromagnetic waves to probe what is the true frequency of these atomic transitions in order to either make these clocks, or we need a few more operations to make the 2 qubits entangle. Now, there's a lot of toolbox available in this platform. For example, one can encode, in fact, not only one set of qubits, but multiple qubits, and one can coherently convert between them. And one can laser cool them to, thanks for the question, these are laser cooled to about a millikelvin, that is 1,000th of a Kelvin above absolute zero temperature. And they can, in fact, be sympathetically cooled. What that means is that you can use a different ion species to use the Coulomb interaction between them to make them cool together. And this is good for certain readout tasks as needed for quantum error correction. Now, they're also highly connected, which means that you can, even with a linearly physically arranged ion trap, you can encode the quantum information in high-dimensional spaces. And this was part of my previous work in New York University, that we put the qubits effectively on a sphere. So how do we entangle them? The way we entangle them, suppose we have a linear chain of ions and we shine 2 laser beams at different directions. Now, that's going to create a differential k-vector, a differential momentum for the ions to see. And so these laser fields not only couples to the qubit degree of freedom, but they also can kick the ions to make them move. Now, when they move, the Coulomb interaction between the charged atoms gets modulated. So this Coulomb interaction essentially acts as a quantum bus, as a motional quantum bus. And we then eventually trace out the motional bus to leave the ions entangled. So with that, we were working on all sorts of quantum simulation experiments, equilibrium, non-equilibrium. One of them was dubbed time crystals. It was particularly discrete time crystals, which was a periodically driven system, which shows shows effects, shows physical observables repeating itself every 2 periods or multiple periods. So essentially, a subharmonic behavior. Anyway, and with this system, as I mentioned, you can get more than 3/9 of 2-qubit gate fidelities and more than 300 qubits, but currently they're not in the same trap. What I mean by that is that in the US, there are already 2 places, the company Continuum and also the Georgia Tech Research Institute. They can get to more than 3/9 of fidelity. And in Tsinghua University, they can get to more than 300 qubits. In fact, I heard that they already have more than 1,000 qubits in Lu Mingduan's group at Tsinghua University. But the problem is that if you want both, if you want best of the both worlds, it's very difficult. The reason is that the Coulomb interaction kind of couples everybody. So it's a bit like when I'm talking to you, this audience, everybody hears what I say, then it gets hard to talk to a single person, one by one, right? So it's kind of a crosstalk challenge that motivated this QCCD, quantum charge coupled device architecture. It looks a little bit complicated. It is complicated to realize experimentally. There's 300 electrodes in vacuum that one needs to connect in order to build this 52 physical qubit. I believe they have now 56 physical qubits. And the idea is that at any given time, you only perform gates on 2 and 2 ions only. And then in order to run a circuit, you have to physically move the qubit around, in this case with electric fields, which is why one needs so many electrodes, because the ions are separated by only a few microns, like 3 to 5 microns typically, so that you have to make electrodes that small in order to create a local field that one ion sees and the other ion doesn't. So it's fairly complicated to get this trap going, and as of 2 years ago or so, they already have 200 people working on this. That's kind of hard to imagine in a university or a research lab.
So let me ask you some very basic questions.
Please. Yeah.
Previous slide, you said it's very hard to listen to one person.
Mm-hmm.
Why do we need to listen to one person?
Well, I guess that's kind of what we.
Don't you want to listen to all of them together because of superpositions?
So that's kind of that's a very good question. In fact, I've always wondered about that. But unfortunately, the current model of quantum computing says that, at least the circuit model says that you have to perform a gate between, let's say, 1 and number 99, and then you run another gate and so on and so forth. So. That's right, and essentially, for example, in some cases, you can make a 3-qubit gate, sort of analogous to the Fracting gate, Toffoli gate, for example, in classical computing, but it's not the main pursuit at the moment. Yeah. So when you want to couple everybody together, it just doesn't quite fit into the computing sort of theory at the moment. So this is why I think not only myself, it's my opinion is that it's very important for theory and experiment to work together to come up with some better model, because we might be tricked by this classical computing model. And so I'll give you one example. I'm not an expert in machine learning, but when I look at these new NVIDIA graphic cards, right, they've ditched the 16-bit float point number. They keep truncating, right? So this is the different dimension. This is the precision dimension. But the point is that machine learning is such a different way of computing that the hardware is also built very differently than the original CPU architecture. So it's very likely, very possible that if you come up with a better quantum computing architecture, that'll make the experiment much easier. Yeah.
I see. And maybe in the next slide, naive thing. So I'm kind of interested to understand what is that picture? X1 bar, X1T. What is that? What does it say?
Huh?
Z1 bar, Z1, Z2, that one. Yeah, this graph. 1, 2, 3, 4, 5 to
that's
K.
so this is a work they in fact have not posted the paper yet. Well, this is probably measuring some. I got a screenshot from a YouTube talk. This is probably some sort of stabilizer or correlation measurement, some parity measurement or something. But they haven't published this. They used 52 physical qubits to encode 50 logical qubits. So that's very high encoding rate. And this is another point, actually. So in fact, there's no one single quantum error correction algorithm that everybody agrees is the best algorithm. That doesn't exist. So that's a rapidly developing field as well. So Professor Liu also has some new developments which might turn out to be very powerful. So we're in fact looking forward to try some of those in the future. Yeah. So I want to talk about now. Switch gears to atoms in optical. Sorry about the typo. In optical tweezers. Oh, sorry about that. Which has excellent scalability. This is based on the technology that was developed sort of in the late 90s, and the first Chinese American person, Stephen Chu, was given the ICBS award this year. So this was Nobel Prize in 1997, and I was lucky enough to have kind of a co-advised in my PhD by Bill Phillips, that what they've done is that they've demonstrated laser cooling of neutral atoms to very cold temperatures, which enabled later Bose-Einstein condensates, and using optical lattices to control atoms. And these tools nowadays, which has single atom imaging, so what you see is an array of about 1,000 atoms, 30 by 30, and one can use so-called magic wavelength, and we will use some of these in our labs to enhance some measurement schemes. So this is kind of a quick gloss over. Let me guide you through how these atoms are trapped in optical tweezers. Yeah. So we first start with an ensemble of laser-cooled atoms with 6 laser beams, for example. And then we use a high-resolution objective to focus light into a very tiny spot, about a 1 micron in radius, so 2 microns in diameter. And if we can generate an array of tiny focused laser beams, then each one of them can, in principle, hold 1 atom. But the problem is that when we initially fill these tiny traps with from the ensemble, they are stochastically loaded. That is, there's a probability on average 50 to 60%, depending on the atomic collisions. But they're stochastically loaded, sort of like this. I don't know if you can see it on the back. I guess the screens. And then one has to take an image and remove this classical entropy by physically moving the atoms into a unity filled array. So there's a classical feedback already applied, and with this kind of the state of the art right now. I showed you this picture before. This was done by Atom Computing, which is a US company. Realized more than 1,000 atoms that is close to defect-free. And in University of Science and Technology of China, they have a new 2D moving algorithm because before people were moving line by line, sort of 1D, and stack them together. And in USDC, they moved the atoms in 2D in order to get this 2024 atoms unity filled. And the state of the art in terms of scale is 6,100 atoms by Manuel Andres' lab at Caltech. They have also demonstrated a 12.6 second coherence time, but note that this array is not unity filled. They haven't done the rearrangement yet. So, of course, Harvard group by Michel Lukin and collaborators were the pioneers, and also there's groups in Germany and France who are also working on this. So the toolbox available for example, 2-qubit entangling is called the Ripper blockade, which basically means that the Ripper level is a highly excited level of the atoms, and when you have one atom excited to that level, the other atom that is physically close enough, for example, 2 microns, will feel the electron cloud of the other atom, and the energies will get shifted so much that the second atom won't be excited. So this creates a conditional logic that one can use to realize C0 or CZ gates. And so the parallel gate operations demonstrated, pioneered by Michel Lukin's group at Harvard, relies on the fact that you have an entangling zone where the Ripper laser shines from 2 directions, and one can have pairs of atoms simultaneously entangled with this global laser. So that's a very highly efficient way of realizing, for example, transversal gates as needed in some quantum error correction codes. So they have a zoned architecture. So I mentioned this entangling zone, and there's a storage zone where you can have qubits that are just lying there with coherence preserving operations. And then there's a readout zone to measure the qubits. So this zone architecture makes realizing logical qubits with lots of physical qubits possible. And this was work done by the Harvard group last year, where they realized entangling multiple, for example, in this case, color code logical qubits, and in this case, the sampling tasks. So, so this is a rapidly evolving field, and in fact, in China, many groups are working on these neutral atoms. A lot of them are building new labs, just like us in BIMSA. And I want to then talk about some applications and some challenges before telling you about our specific plans here at BIMSA. Are there any questions before I move on?
Yeah, so why did you move the atoms?
So you have to move the atoms in the first place because of the classical entropy removing, right? And in terms of quantum circuits, so in terms of quantum circuits, you don't exactly have to move the atoms. You can use the, for example, the surface code architecture, much like the superconducting qubits. There are 2 problems. One is that the surface code, which is independent of any physical platform, the surface code still has very low encoding rates. You still have to have many hundreds of atoms to encode 1 logical qubit if you want an error to be really low. There's another problem which is unique to the Ripper, which is the fact that this Ripper interaction mechanism, I told you, that the one atom has such a big electron cloud that affects the other atom. This is slightly non-local. It's not like the Coulomb interaction in ions, which is very delocalized. This Ripper interaction has van der Waals, which is 1/r⁶ decay. It actually depends on the state you choose. It can be anywhere between 1/r³ to 1/r⁶, but it's slightly non-local. So you will have a leakage or crosstalk into neighboring qubits if you give it a grid kind of pattern. Yeah. So, but there are. That's a very good question. There are people pursuing that approach. Yeah. Anyway, okay. So I want to talk about applications and challenges, but this is a really brief discussion because I would say that the applications and the challenges, um, the open challenges are up to both the experimentalists and the theorists. So there are many proposed applications of quantum computing. Some of them are near term, such as, for example, combinatorial optimization. Example algorithm include quantum approximate optimization algorithm, basically trying to solve graph optimization problems, such as traveling salesman, right? With approximate quantum algorithms. So this is, in fact, people are hoping that there's, to my knowledge, there's no rigorous proofs. So people are hoping that some of them might work better than classical computing, but we really have to try it out. It's a bit like machine learning. It works when it works. So we have to try. There's quantum chemistry simulations. But most of the algorithms I'm aware of requires at least 10 to the 9, if not 10 to the 14 gates. So the gate model really puts a quite heavy overhead on the precision that is needed. We are quite a bit far away from 100 logical qubits and 10 to the minus 14 error per 2 qubit gates. So I would say that quantum chemistry might have some relations to do with quantum simulation. For example, some of the equilibrium dynamics that I showed you before. That might be a bit of a stretch, but not too much. The problem with quantum simulation is that one is usually fixed to a certain model. For example, you have a long-range interacting spin model, such as Ising model or Heisenberg model. It's not like a universal computing that is very programmable. So that's a bit of a problem with quantum simulations.
By the way, sorry to interrupt you.
Yeah,
We asked so many questions, but
yeah,
it's good
yeah,
if we can have 5 minutes also Q&A. So right now, in 3 minutes, it would be 5 minutes Q&A.
Okay, okay. So, and there's a lot of discussions about artificial intelligence and how we can use quantum to enhance that. So far, what we see is more like AI for quantum, which is AI can in fact help us learn what the error rates and better algorithms and so on and so forth. So I won't go into details for the interest of time. I will just emphasize that ion traps are precise but lacks a truly scalable architecture, whereas neutral atoms in optical tweezers in fact suffers from losses. That these optical traps are very shallow, and every now and then you will have a few atoms missing from the trap. So although you can have very large numbers, detecting these losses and replenishing the atoms and replenishing the quantum coherence is a bit of a challenge, but there are ways to deal with that. So lastly, I want to tell you, because it's been a couple of months since I moved to BIMSA, and the plans here, I want to work on some of the architectures associated with ion traps, and I want to primarily focus on neutral atoms. The goal number one will be to start with quantum simulation of, for example, spin models, and the long-term goal will be truly fault-tolerant quantum computing. The platform that we have chosen the cesium atom, which is the same atom that was used in the 6100 atom paper. And we believe that there should be ways to go beyond 10,000, maybe even reaching close to 100,000 atoms. Now, once you have the scale, then scale is not the problem. You have to have the precision. Now, there are ways to improve the 2 qubit gates, and I want to emphasize that not only that, there's a measurement problem that cannot be cannot be neglected, which is the fact that currently in neutral atoms, for example, in the Harvard works, phenomenal works, there's a one catch. That is the atoms, once they are being measured, on average, 50% of them are lost. So if you want to correct many rounds in a QEC code, you have to throw away a lot of ancilla qubits when you want to make a circuit run. So with the cesium atom, one has a so-called magic wavelength at a convenient wavelength. We just got this laser installed as of last Friday. That we can have the same star shift for the ground state and excited state atoms, and so that will make the measurement problem a lot easier. That is, there was a paper done by U.S. Sandia National Labs. They can achieve 3 nines of measurement fidelity with only less than 1% atom loss. So that's a factor of 50 better than the Harvard results. So I'm very optimistic that we can build interesting quantum systems that can perform quantum information experiments. So this is our current progress. We just moved into the temporary lab in A7. So anybody interested in taking a look, welcome to contact me. And we have an ultra-high vacuum system installed with 10 to the minus 11 torr level of pressure that is close to the between the Earth and the Sun, the vacuum level. So which are very good for cooling the atoms, which we are preparing for the laser cooling to be performed. So the temperature, okay, so this machine is room temperature. But the atoms in there will be cooled to millikelvin above absolute zero. Yeah.
Amazing.
Okay.
All
so
right.
With that, thank you very much. And
thank the speaker.
Also, thanks to the new group members recently joined. I have intern students and engineers. Yeah.
Okay. Any basic questions? Basic. Don't ask detailed questions. Not possible.
Yeah, please.
Yeah.
Thank you. You mentioned that the method you introduced there will be very precise. Like, well, I'm not an expert in this area, but from my maybe it's wrong. From my understanding,
yeah.
Since we are using a complex state, it's continuous. How we need to say if it's 45 degree, how can we make sure you got that degree? Yeah. So when you say
that's exactly the conundrum. I was discussing with Professor Liu that these errors are continuous, but we digitize them by pretending that the errors are only bit flip and phase flip or leakage errors. We classify them into these digital errors. So that's kind of a message, a question that is also mostly, I would say, for theoreticians. Please come up with a better model of quantum computing to make our lives easier and to make quantum computers, come true.
No question.
All right. More questions?
So because I'll just quote Bill Phillips, who said, quantum computers are different compared to, say, laptops. The difference is more than laptops compared to Abascus, because Abascus are Turing machines. So we have quantum mechanics is a completely different model. So that really calls for better computing models.
So can I ask you a very, very basic thing?
Yeah. No.
I still haven't figured this one out.
Please, these are not basic questions. These are important
mine
questions.
is really high school, secondary school level.
No. Please.
Let's say you have this in any scenario. I mean, superconductors or the ion trap.
Sure.
Okay, let's say I want to know 1 plus 1 is 2. Okay, you encode these particles, and then you look at 1 plus 1 equal to 2. So it gives you all possible entanglements, all possible superpositions. So answers could be anything. Okay. At the end, I never understood how do you find the most probable answer is 2. You need to have some ground truth to compare this with. But if I just gave your computer 1 plus 1 without human involvement, how do you know 1 plus 1 is most probably 2? How do you in between? How does the machine know that the most probable answer is 2?
Right. So I think this is a very profound question that classical computers are deterministic, whereas quantum computers, you have to go to these highly entangled states, and if you measure in the middle, it's completely stochastic, right? But you see, some of these algorithms are, in fact, in the end, deterministic. So, for example, the factoring algorithm, right? You do this period of finding. The point is that intuitively, right? Intuitively, you start with an unentangled state, and you evolve into this highly entangled manifold, and then you disentangle everything and arrive at a deterministic answer. So you don't measure in the middle, you measure in the end. But the problem is that if in the middle you have such a highly entangled state that you cannot compute, you cannot reproduce with a classical computer, how do you know it is correct? How do you know the process of the computing is correct? So these are all very interesting questions. I don't have a unified answer to. The QAOA algorithm is not like that. The point is that, for example, you evolve into a state where you do sampling tasks, and most of the results gives you, for example, the ground state of some Ising model, or some desired excited state of an Ising model. And so that is getting probabilistic, but the point is that your final state has to have a high overlap with your answer, right? But then again, you cannot measure in the middle. In the middle of your computing, it's a highly entangled state.
So, okay, let me ask you some questions. 0 and 1. 0 plus 1 is 1, right?
Yeah.
But if I give it to quantum computer, my understanding is like tensor product. I can have 0, 0, 0, 1, 1, 1, 1, 0. Okay. Now I have it. How do I know it is
You need
one,
to choose
1, 0, 1? How do I know it's the answer is 0, 1? It should be 1, right?
Right.
Okay.
So for example, you want to do
even if I de-entangle them, I will have now one state 0, 0, 1, 1, 0, 1, 1, 0. Which one is the answer?
So depends on your initial state, you will get different final results, right? So suppose you want to do a C0 gate, control the NOT. Qubit 1, if it's 1, you flip it. If it's 0, you don't flip it, right?
Okay.
Then if you have a product state to begin with, 0, 0, or 1, 1, or 1, 0, the answer is always going to be deterministic. Okay, but if you had a superposition state, for example, 0 plus 1 to begin with, then you always end up in an entangled state. C0 entangles it, and then when you measure, you get probabilistic outcomes. So it very much depends on your input, your circuit, and your output. Right?
Okay. More questions? I have not gotten my answer, but more questions.
You cannot do any calculation via quantum computation. You can do calculation which you have already algorithms designed for that kind of calculations. Okay.
Addition.
Yeah. Addition. Yeah. No. For example, for sorting or factorizing.
Okay.
If you look at the result.
I'll talk to you too. More questions?
Okay, just a quick precision. When you talk in your experiment about this wavelength 937, going towards IR, it means you understand your hyperfine structure very well, where you pump all your atoms and where they relaxed, which level, right? How do you hold them? So the question is, how do I identify that this wavelength is the one that will allow you to raise this grid to higher numbers?
Wow, that's a very physics question. Thanks for asking. So in fact, you don't have to, because this is a magic wavelength for the cooling transition, which is relatively broad. So we have multiple levels. The hyperfine levels you mentioned lies in the ground state, and that is where we use to encode the qubits, right? And this magic wavelength is for the transition from the ground state to the first excited state, and this transition is what we use for performing the cooling. So in fact, this transition is so broad, it's a few megahertz wide, such that the magic wavelength, you only have to stay within a range. In fact, it's from 935 to 940 nanometers. As long as you stay in that range, you are approximately not start shifting the excited states. You are approximately shifting the ground and excited states by the same amount. So you don't have to be. That's right. There's a range. Hmm?
More questions? Basic questions? Here's a basic question: is your if I may ask, what's the price of your machine?
It's fairly expensive, but
so $10 million.
Oh, that's pretty close estimate. No. It's $10 million if I were to sell them. It's 10 million Chinese yuan if I want to build them. So I see. So I would say that's
so it works like real estate.
It's a bargain compared to these GPU clusters. I promise you, it's a bargain. Yeah, please. Yeah.
Question.
Oh well, there's quite a few companies. There's quite a few companies.
Even more.
Well, if we want to talk business, we can talk about business models. So, in fact, if you go to a ramen store like Lanzhou Lamian, yeah, the cost will be about half of what you paid, or maybe less. So 50% profit margin will be very common for businesses. And in high-tech businesses in the U.S., on average, it's about 3 times. So $1 to make it, $3 you pay for it. So I would say quantum computer, if you charge 3 times the money, the cost of building that machine, that's not a that's definitely still quite cheap. Huh? Well, those are just.
Well, we hope that you succeed, because on behalf of pure mathematicians, if you guys succeed, we can relax.
Right now, we're focusing on
our own research.
Right now, we're
focusing
on basic science. But if you really want to sell these computers, you need a lot more than just the experiment itself. You need a lot more space. You need 200 engineers, like the Quantinuum company, and those costs are all going to enter into this, factor of 7 or factor of 10 difference. They will. Yeah.
Let's thank the speaker again.
Thank you.